Hello, welcome back. And this week's video is going to be about the disk method. And basically, if you don't know what a disk method is, it's a method of finding out the volume of a shape if you take a function and you rotate it around the x or the y axis. Now, if we were to imagine this, say you have a function that goes like this, and you take this aspect of it and you rotate this whole function around in this case, the x-axis. And then this volume right here is what you'll be trying to find. And you can rotate functions around other boundaries, and also you can rotate functions around other functions. But here I'll just be focusing on rotating functions around the x and y axes. So the main idea behind the disk method is that you split your function into little disks that each have an infinitely small depth. And this is going to be your dx or dy. And then you find the area of each of those disks, the cross-sectional area. You multiply this by the depth, also known as dx or dy, and then you sum it all up. This is where the integral sign comes in, and you sum it all up to get the total volume. So I would say these are the main 4 steps: splitting the function into disks, and then each disk having a depth of dx or dy, and then finding the volume for each disk, and then summing all of the disks up, which is like infinitely many disks. So this might seem a bit fuzzy and rather confusing if you're just thinking about it. I understand. We need to visualize this, and that's exactly why we're going to do a couple of examples. So this is a function, your very basic parabola. This is y equals x squared. And the first thing we're going to do is we're going to rotate this around the x-axis. So if we rotate this around the x-axis, we can imagine something like this. We're always going to have it be a reflection, so like that. And then, for example, here it's 2 away, and so on and so on. And then we end up with a shape that looks something like this. And I know this looks rather confusing, but if you imagine it, it would be somewhat like this, where this is your shape and it just goes like this, and that is like that. And you want to find the volume of this shape. So how we might go about this is we recognize that if you look at the shape, you can take out a little disk from it, like I've talked about. So let's take this disk right here that makes up this shape. And the depth of this is going to be dx, right? Because as we take a depth that goes infinitely small, right? You're going to end up with a dx. And then you will also recognize that this is a circle, right? Because we're rotating this around. So that means around the x-axis, that means the distance from a given point on the function back to the x-axis will always be the same because it's a rotation. So that we also know that if we take this out, we can imagine this as being a circle, where this is your x-axis, right? And this is your radius. And your radius, in this case, is just going to be x squared. This value right here is x squared. You're just getting x squared, right? You can also just say that this is your y. Let's say that f of x is equal to this function. So this is just going to be f of x. So first we find the area, and we know that the area is pi r squared, right? So the area is pi times f of x squared. And in this case, area is going to be pi times x squared squared. So it's going to be x to the power of 4 times pi. That's going to be our area. Now our volume is going to equal to area times depth. And once again, like we've said, our depth is d of x. So it's going to equal to x to the power of 4 times pi times dx. And then lastly, our total volume is going to equal to the sum of all of these depths from 0 to 4, like specified over here, of x to the power of 4 times pi dx. And we can take this pi out because it's just a factor and it's easier to work this way. And this is going to be our expression. So if we solve this, we're going to have pi where we take x to the power of 5 over 5 from 4 to 0. We end up getting 204.8 pi. So this is going to be our volume for this case right here. Now, what if we take this same function but rotate it around the y-axis instead? So in this case, we're going to rotate this function, x squared, around the y-axis, and we're going to find the volume from y equals 0 to y equals 5. And if we imagine this, we end up getting a shape that looks somewhat like this, right? Where each little disc or each little ring fits together to create one big shape that might look like this. This would be the solid. And we're trying to find its volume. How might we approach this? Well, we're going to view this shape as a lot of little discs put together. Except here, the depth is not dx. No, the depth is dy, because we're rotating around the y-axis. So therefore, we're not taking the depth like this. That doesn't make sense. Our depth is in reference to the y-axis. So our depth is going to be dy. And this means we're going to have to find the integral in terms of y. But this also makes sense, because if we look at the shape as a circle, we see that the center point is the y-axis. So the radius is not the y value. The radius is the x value. So this is going to be the x value. But it's not just simply x. It's x in terms of y. So first, we rearrange this function and find out what is the value of x in terms of y. And here it's pretty simple. X is equals to the square root of y. So we're going to end up working with this function right here instead, because once again, the radius in this case is the x value, but the x value can be expressed in terms of y in order for us to find it, right? Let's go with the same strategy. First, we find the area for each little piece. Area is equals to pi r squared. In this case, it's going to be pi times square root of y squared, so it's going to be y times pi. Then each little volume is going to be equal to area times depth, which is going to be equal to y times pi times dy. And then lastly, over here, we're going to find the total volume, which is going to equal to the integral, because we're summing all of them up, from 0 to 5, because once again, we're doing it in reference to the y-axis, and this is like how big our shape is, y times pi times dy. And once again, we can take this pi out because it's simply a factor, and if we solve this, we're going to end up getting 1/2 y from 5 to 0 times pi. We're going to have 12.5 pi. This is going to be our final volume, 12.5 pi. So I hope you understand how this works. And let's look and try to generalize what we're doing over here so we can put it into a formula. So when we're rotating around the x-axis, the first thing we do is we recognize that the depth is dx. Other than that, we first find the area. And to find the area, we have to know the radius. And the radius in this case is simply the function itself. The radius can be defined as the function itself. So if we want to generalize this, when we rotate around the x-axis, the volume is going to equal to the definite integral from a to b of each little volume. And how can we express each little volume? Well, it's pi r squared, right? And our r squared is simply the function. So we're going to have f of x squared times pi, and I'm taking the pi out because it's just a factor, dx. So this is going to be the expression, or so to say, our formula. And then if we do it around the y-axis, it's pretty much going to be the same thing. Volume is going to equal to the definite integral from a to b, but in this case, our function is not going to be in terms of x, our function is going to be in terms of y, because our depth is dy, so we have to do all of the other calculations in terms of y as well. So our volume is going to be, once again, pi r squared, where we take this pi out, and our radius is going to be f of y, dy. So here you can see that we're working with x's in terms of x's because the depth is a dx, but here we're taking the same function but in terms of y because the depth is also dy. So I hope these generalized formulas make sense, and I hope you understood what this disk method really, how it approaches this problem of finding a volume of a function that is rotated to give you a solid. So I hope you understand, and you will gain more understanding the more examples you do. And I think it's really important to visualize this, because as soon as you visualize and you realize where each disk is and what you have to do to find the area or then the volume, it's really logical how this approach was made and where it comes from, because all it does is simply breaks down the shape and then adds all of the little pieces together. So I hope you enjoyed this video, and see you next week.